Hi everybody, welcome to a new machine learning from scratch tutorial. Today we are going to implement the naive Bayes classifier using only built-in Python modules and NumPy. So the naive Bayes classifier is based on the Bayes theorem, which says that if we have two events A and B, then the probability of event A, given that B has already happened, is equal to the probability of B, given that A has happened, times the probability of A divided by the probability of B. And if we apply this to our case, then our formula is the probability of Y, of our class Y, given the feature vector X, is equal to the probability of X given Y times P of Y divided by P of X, and where X is our feature vector, which consists of several features. And now it's called naive Bayes because now we make the assumption that all features are mutually independent, which means, for example, if you want to predict the probability that a person is going out for a run, given the feature that the sun is shining and also given the feature that the person is healthy, then both of these features might be independent, but both contribute to this probability that the person goes out. So in real life, a lot of features are not mutually independent, but this assumption works fine for a lot of problems. And with this assumption, we can split this probability into and use the chain rule. So we calculate the probability for each feature given Y and multiply each. And then we multiply it with P of Y and divide it by P of X. And by the way, this P of Y given X is called the posterior probability. P of X given Y is called the class conditional probability. And P of Y is called the prior probability of Y. And P of X is called the prior probability of X. And now we want to make a classification. So given this posterior probability, we want to select the class with the highest probability. So we choose Y, which is the argmax of Y of this posterior probability. And now we can apply our formula. And since we are only interested in Y, we don't need this P of X, so we can cross this out. And then our formula is this, so Y is the argmax of, and then we multiply each class conditional probability and then the prior probability. And then we use a little trick. Since all these values are probabilities between 0 and 1. So if we multiply a lot of these values, then we get very small numbers and we might run into overflow problems. So in order to prevent this, we apply the log function. So we apply the log for each of these probabilities, and with the log or the rules for logarithms, we can change the multiplication sign into a plus sign. So now we have an addition here. And now we have this formula that we need. And now we need to come up with this prior probability. So the prior probability is just the frequency. We can see this in a second. And then what is this class conditional probability? P of X given Y. And here we model this with a Gaussian distribution. So here we can see the formula. So this is 1 over and then the square root of 2 pi times the variance of Y times the exponential function of minus x minus the mean value squared divided by 2 times the variance. And here we see a plot of the Gaussian function for different means and variances. So this is a probability that is always between 0 and 1. And yeah, with this formulas, this is all we need to get started. So now we can start and implement it. And first of all, of course, we import NumPy as NP. And then we create a class called naive Bayes. And it doesn't need an init method, so we can implement the fit method first. So we want to fit training data and training labels. And then we also want to implement a predict method. So here we predict the test labels or test samples. And now let's start. So let's start with the fit method. So what we can do here is, so we need the priors and we can calculate them in this fit method. And we need the class conditional. So here we need the mean for each class and the variance for each class. So we can also calculate these. So let's do this. So let's get the number of samples and the number of features first. And by the way, our input here, the x is a NumPy ND array, where the first dimension is the number of samples and the second dimension, or the number of rows, is the number of samples and the number of columns is the number of features. So we can unpack this and say this is x.shape. And our y is a 1D row vector, also of size the number of samples. So this is our input. And now let's get the unique classes. So let's say self classes equals NumPy unique of y. So this will find the unique elements of an array. So if we have two classes, 0 and 1, then this will be an array just with one 0 and one y in it, and one 1 in it. Then let's say the number of classes equals the length of this self classes. And now let's init mean, variance, and priors. So let's say self.mean equals, and we want to init them with zeros at first. And it gets the size. It has number of classes and number of features as tuple here. So it also, for each class, it has the same number of for each class we need means for each feature, and we want to get this or give this a data type of float numpy.float64. And we want to do this with the same for the variances. So let's say self.var equals this. And then we want to do self.priors equals np.zeros. And here for each class we want one prior. So this is just a 1D vector of size number of classes with a data type of np.float64. And now let's calculate them. So for each class in self.classes, we only want the samples that has this class as label. So let's call this xc equals x, and then where c equals y. And now we can calculate the mean for each class and fill our self.mean. So we want to fill this row and all columns here, and we say this is x c dot, and NumPy has a ND array has the built-in mean function, so we can say mean along the axis 0. So please check the mean function for yourself. And we want to do the same thing for var, so self var. In this row, for each column is xc.var, so NumPy also has a var method. And then we calculate the priors, so self priors of this class is equal to, and now what information do we already have if we have the training samples and training labels? So we can say the prior probability that this class will occur is equal to the frequency of this class in the training samples. So we say we get xc dot shape 0, so only this will get the number of samples with this label, and then we divide it by the number of total samples. So, and we have to convert this to a float because we don't want integers here. So let's say float number of samples. So this is the frequency, how often this class C is occurring. And now this is all for our fit method. And now let's implement the predict method. So, and for this we create a little helper method. So let's call this underscore predict self, and this will only get one sample. So here we have we can have multiple samples. So here we say y predict equals, and then we use list comprehension and call this underscore predict method for only one sample, and then we do this for each sample in our test samples, and then we return them. And now we have to implement our underscore predict method. So here what we need now is we need to apply this function. So we have to calculate the posterior probability and calculate the class conditional and the prior for each one, and then choose the class with the highest probability. So let's create an empty list called posteriors equals an empty list. And now let's go over each class. So let's say for index and C in enumerate self.classes. So here we get also the index and the class label with this enumerate function. And now we can say first we get the prior. So the prior equals, and we already have calculated the priors. So this is the prior of self dot priors with this current index. And now, as I said, then at the end we apply the log function. So let's apply this right here. So let's say np.log, and then create the posterior. So the posterior equals, or let's call this class conditional equals, and then we apply the Gaussian function. So for this, let's create this helper function and call this probability density function with self, and then it gets the class index, and then it gets x, and here we apply this formula here. So we need the mean and the variance, and then apply this function. So first of all, let's get the mean equals, and we already have the mean, so we can say self mean of this class index, and also the variance equals self var of this class index. And then let's create the numerator, which is equals to numpy dot exp, so the exponential function of minus, and then we have x minus mean to the power of 2 divided by, and then 2 times the variance, and then we have the denominator, so denominator equals, and here we have np dot sqrt, so the square root of 2 times, and we have pi. We can also get this from numpy, np.pi times the var, and then we return numerator divided by denominator. So this is our probability density function, and then we can say our class conditional is self dot probability density function of our index and x, and then we want to have the logarithmus, so we say np.log, and then we sum all of them up. So we can use numpy.sum of this, and then we say our posterior equals prior plus the class conditionals, or class conditional, and then we append them to our posteriors. So posteriors dot append posterior, and now we use, or we apply the argmax of this and choose the class with the highest probability. So NumPy also has a argmax function, so this is very easy. So we can now say return self dot classes of, and the index is now the index of the posteriors with the highest probability. So we can say np.argmax of this posteriors, and now we are done. So this is the whole implementation, and now we can run it. So I already have a little test script where I use the scikit-learn library to load a data set and create a data set with 1000 samples and 10 features for each sample, and we have 2 classes. Then we split our data into training and testing samples and the labels. Then we create our naive Bayes classifier, which I import from this file that I have here. And then I fit the training data and the training labels, and then I get the predictions for the test samples, and then I will calculate the accuracy. So let's run this and see if this is working. So yeah, it's working, and we have a classification accuracy of 0.96. So pretty good. So yeah, that's it. I hope you enjoyed this tutorial, and see you next time. Bye.